We mentioned the notions of multiplicities, the algebraic multiplicity and the geometric multiplicity of an eigenvalue. Now I want to define them formally and state the theorems that relate to them formally. I'm not going to prove them. And we're going to do some more examples. So here's the definition. First thing, let alpha be an eigenvalue. An eigenvalue of a linear map T from V to V, or of an n by n matrix A, doesn't matter. Okay, it's an eigenvalue. The algebraic multiplicity of alpha, the algebraic multiplicity of alpha, is the number of times it appears as a root of the characteristic polynomial, equals the number of times blah. The number of times alpha appears as a root of the characteristic polynomial. By the number of times, I mean when you factor the characteristic polynomial, when you factor into linear factors, how many linear factors are of the form alpha minus that alpha naught, or the specific value. Okay? Is it clear what I mean by the number of times it appears? Not that you do it 7 times and you see it every time. Okay, that's good, everybody? Okay, so that's the algebraic multiplicity of alpha. The geometric multiplicity of alpha equals, so this is the geometric multiplicity, is how many eigenvectors, how many linearly independent eigenvectors correspond to alpha. So the number of linearly independent eigenvectors corresponding to alpha. This can be said in various ways, right? It can be said is the dimension of the null space of A minus alpha I. Or the number of degrees of freedom in the solution set of the homogeneous system A minus alpha I times V equals 0. Okay? This is all different ways of saying the same thing. So is it clear what the algebraic multiplicity and the geometric multiplicity is? Okay? I still have on the board the summary of the previous example, which we did in the previous clip. Let's glance at it quickly. This was the matrix we started out with. We found 2 eigenvalues. One was -2, the other was 4. -2 appeared twice. The characteristic polynomial was alpha plus 2 times alpha plus 2 squared times alpha minus 4. So -2 had algebraic multiplicity 2, and 4 had algebraic multiplicity 1. -2 contributed 2 vectors to the basis, v1 and v2. These are 2 linearly independent vectors, which both satisfy that A times v1 equals -2 times v1. And A times v2 equals -2 times v2. And they're linearly independent. Okay, so they're both eigenvectors corresponding to -2. Therefore, -2 had geometric multiplicity 2 as well. Whereas 4 had geometric multiplicity 1. It only contributed 1 vector to the basis. Okay, so that was the case in this example. Good? Okay. Here's the theorem concerning eigenvalues and eigenvectors. So it's going to have two parts. One, for every eigenvalue, alpha, the geometric multiplicity is always less than or equal the algebraic multiplicity. So algebraic multiplicity is always greater than or equal to geometric multiplicity. That's the first part of the theorem. So the geometric multiplicity cannot exceed the algebraic multiplicity. If it appears 7 times as a root, it can contribute at most 7 linearly independent vectors. Okay? It's a non-trivial statement to prove. The proof is not a two-liner. Okay? I'm not going to prove this theorem. Okay? 2 says the following. A is diagonalizable, or T, if you're looking at a transformation, diagonalizable, Every time I write this word, I feel like adding letters. I don't know why. I feel like adding like diagonalizable, Asianism, or something like that. It's just a never-ending word. Okay, A is diagonalizable if and only if the characteristic polynomial factors over whatever field you're working, over F. So it really breaks up into linear factors. By factors, I mean into linear factors. So it factors into linear factors, meaning you have all the alphas you need. Okay? And each alpha contributes enough eigenvectors. And the algebraic multiplicity equals the geometric multiplicity for every alpha. So factors means there are enough alphas. And this means that each of the alphas contributes its duty, the load of vectors it has to give in order for constructing a basis with enough vectors. Okay? Clear? That's part 2 of the statement. It's significantly easier to prove once you know part 1, but you still have to work a bit there. Okay?
You said you're not going to prove part 1. Is that because
I'm not going to prove both of them. We have to.
Because of time or because we're not?
No. In terms of intelligence, you can easily see all the proofs, if that's the question. There's nothing hidden in this course that's too complicated. Really not. This course has a certain scope of material that we have to cover, and the price is that we can't, to cover over a given amount of time, the price is that we can't prove everything. And usually, well, it's a good time to ask this towards the end of the semester, but usually I try to prove either things that are very elementary, okay, or things that hide ideas which are important to duplicate later in other proofs of exercises or examples or whatever. Okay? We can't prove everything. We have to choose what to throw out in terms of proofs, and I'm not proving this. Okay? Okay, so this is this theorem. Let's write down some examples. So the first example is, let's call it example 1. Let's look at the matrix A equals 0, 1, negative 1, 0 over the field R. So this is a real matrix, 2 by 2. What can we say about it? So what's its characteristic polynomial? The characteristic polynomial is the determinant of A minus alpha I. That's the characteristic polynomial, right? So what is it? So it's minus alpha, 0 minus alpha I, 1, negative 1, minus alpha. It's this determinant. That's the characteristic polynomial. Do you agree? So what do we get? We get minus alpha times minus alpha. That's alpha squared. Minus 1 times negative 1. So minus minus 1, so it's plus 1. That's the characteristic polynomial. This is P of alpha for this matrix. And this polynomial is irreducible over R. It doesn't factor into linear factor. It doesn't have roots, real roots. It has complex roots, right? I and minus I. But if we're working over R, it doesn't have roots. Do you agree? Okay. So saying that it doesn't have roots means that there are no eigenvalues for this matrix over R. And in particular, it's not diagonalizable. Okay? So P of alpha has no real roots. Hence, A is not diagonalizable over R. Okay? Now, if you work over the field of complex numbers, it is going to have roots, I and negative I. Okay? And it is going to be diagonalizable over C. Okay? And you can find its diagonal form over C. You're going to have complex entries. Okay? Good? So this is an example where it's not diagonalizable because we don't have enough alphas. We're not even down to the situation of verifying that each alpha contributes enough vectors. We just don't have enough alphas. Clear? Okay. Let's look at another example. Example number 2. Example number 2 is again going to be a 3 by 3 matrix. And what we're going to find out there that there are going to be alphas, but they're not going to have big enough geometric multiplicities. They're not going to be able to contribute sufficiently many vectors to form a basis. So here's example number 2. Let's look at the matrix. I'm going to call it B. And it's going to be the matrix -3, 1, -1, -7, 5, -1, -6, 6, and -2. This is the matrix B. As a linear map, what are the domain and the range? You better be able to answer this now.
3 tuples.
3 tuples, good. So if we're working over R, it's a map from R3 to R3. Good? Thank you. Okay, let's find the characteristic polynomial. Okay, so the characteristic polynomial is the determinant of B minus alpha I. This is the characteristic polynomial, right? And we want to find its roots. Those are going to be the eigenvalues. So what is B minus alpha I? So it's the determinant of the matrix, subtract alpha from the main diagonal. So it's -3 minus alpha, 1, -1, -7, 5 minus alpha, -1, -6, 6, and -2 minus alpha. That's the determinant we have to calculate. Once again, not stubbornly, but wisely. Okay? First do row and column operations carefully, such that when you eventually calculate the determinant, you're going to have it factored. Okay? It's just a better approach. So the first thing I'm going to do, again, is add column 2 to column 1 in order to have a 0 here. So what I'm going to get is -2 minus alpha, right? I'm adding a 1. -2 minus alpha, 0, 1, 5 minus alpha, 6, -1, -1, -2 minus alpha. Tell me if you agree. I added column 2 to column 1. I'm going to pull out this 2 plus alpha with a minus sign here. So there's minus 2 plus alpha here. And I'm left with 1, 1, 0, 1, 5 minus alpha, 6, and negative 1, negative 1, negative 2 minus alpha. Good. And once again, I'm going to subtract row 1 from row 2. Okay, so I'm going to get a 0 here. So I'm getting, there's this, sorry, negative 2 plus alpha. And I have, where is it? 1, 1, negative 1, 0, 4 minus alpha, 0, and 0, 6, negative 2 minus alpha. Do you agree? Now I'm going to calculate the determinant using the first row, evaluate it using the first row. So I'm going to get 1 times this minor, and this minor is just the product of 4 minus alpha and negative 2 minus alpha. So what I get is that P of alpha, the characteristic polynomial, is negative 2 plus alpha times another one. So it's 2 plus alpha squared times this 4 minus alpha. Do you agree? Does it look familiar? Okay, so it's the exact same characteristic polynomial that we got in the previous example, in the previous clip. Okay, let's look back again at this board. It's the same characteristic polynomial we got here that had negative 2 as a double root with algebraic multiplicity 2 and 4 as a root with multiplicity 1. Okay, same characteristic polynomial. Automatically it follows that it has the same eigenvalues, right? The eigenvalues are the roots of the polynomial. So if these two matrices, A and B, have the same characteristic polynomial, they have the same eigenvalues. Okay? So the eigenvalues, so note that A from the previous example, from the previous lesson, not that 2 by 2 example with no roots, A from the previous lesson had the same characteristic polynomial. Okay, good? Okay, so now we know the alphas. Alpha equals negative 2 is a root, therefore an eigenvalue, of multiplicity 2. It appears twice, 2 times. And 4 is a root of algebraic multiplicity 1. It appears once as a linear factor. So we do have enough alphas. It did factor, okay, into linear factors. Question is, what are the contributions of each in terms of the null spaces? How many eigenvectors can each of these contribute? What is the dimension of the kernel of A minus alpha I for each of these? Good? Okay, so let's look at that. So let's leave this theorem. Let's erase here. Okay, so let's start with alpha equals negative 2, just like we did before. Alpha equals negative 2. And let's find eigenvectors corresponding to it. So B minus alpha I, now it's B, and now alpha is negative 2, is the matrix. I'm just writing what it is. So it's negative 3 minus negative 2. And then 1, negative 1, and negative 7, 5 minus negative 2, negative 1, and negative 6, 6, and negative 2 minus negative 2. This is B minus negative 2i. Okay? And when I calculate these numbers, I get negative 1, 1, negative 1, negative 7, 7, negative 1, and negative 6, 6, 0. This is b minus alpha I. And I want to solve the system. I want to find the kernel of b minus alpha I. I want to find the solutions to the homogeneous system. Negative 1, 1, negative 1, negative 7, 7, negative 1, negative 6, 6, 0, x, y, z equals 0. I need to solve this. Non-zero solutions. Non-zero solutions are the eigenvectors. Good? Everybody clear on what we're doing, why we're doing it? Okay, wonderful. So let's do it. If we know why and how, let's just do it. So I'm going to take the coefficient matrix and start doing row operations. So negative 1, 1, negative 1, negative 7, 7, negative 1, negative 6, 6, 0. Start doing row operations, only row operations, right? I'm solving a system. So what I'm going to do is take R3 to be R3 minus R2 plus R1. R3 minus R2 plus R1 would make this a 0. That's the goal. So I get, I'm not touching the first two rows, negative 1, 1, negative 1, negative 7, 7, negative 1, and tell me if you agree that it just so happens that I get a row of zeros. Do you agree? Okay. So in principle, I can continue to the echelon form or to the canonical form and so on. But already at this stage, I can see that these two remaining non-zero rows are linearly independent. One is not a multiple of the other. Do you see that? Okay. So the rank of A, or sorry, the rank of B minus negative 2i, the rank of this matrix is 2. Okay. So we already see here that the rank of B minus negative 2i equals 2. Do you agree? We don't need to continue at all. If it's 2, if the rank is 2, what's the dimension of the null space? 1. Do you agree? That's the rank nullity theorem. So the dimension of the kernel of B minus negative 2i is 1. Do you agree? That's the rank nullity theorem. So how many linearly independent solutions are there going to be to this system? 1. So what is the geometric multiplicity of alpha equals negative 2? 1. So we don't even need to find it, because that's it. We're doomed. B is not going to be diagonalizable. Okay? The geometric multiplicity of alpha equals negative 2 is 1. Which, this 1 has a property that it's strictly less than 2. And 2 was the algebraic multiplicity of negative 2. Okay? Therefore, B is not diagonalizable since the theorem doesn't hold. Let's say this again, because it's a mouthful of ideas. The rank, we try to solve this system, solutions are eigenvectors. Non-zero solutions are eigenvectors. This is b minus alpha I, where alpha is negative 2. We found, after a single step, that the rank of the coefficient matrix is 2. If the rank of the coefficient matrix is 2, the null space, or the solution space, is of dimension n, 3, minus the rank, 2, which is 1. So the dimension of the null space, which is a different name for the kernel of this matrix, is 1, right? Therefore, there can only be one linearly independent vector solving this. There's only one degree of freedom. Good? Therefore, the geometric multiplicity, by definition, how many linearly independent vectors are there? Or, what is this dimension? Same thing. The geometric multiplicity of this eigenvalue, negative 2, is 1. Whereas the algebraic multiplicity of this eigenvalue was 2. So there's a strict inequality here. And our theorem said, look at this board please, A is diagonalizable, but that's also true for B, right? B is diagonalizable if and only if the characteristic polynomial factors over f. This happened. And the algebraic multiplicity and the geometric multiplicity are not just less than or equal to, but they're equal for every alpha. And in this case, we found an alpha for which this is 1 and this is 2. So they're not equal for every alpha, therefore it's not diagonalizable. Clear? So back to this board, therefore B is not diagonalizable since the theorem doesn't hold. Clear? Everybody? Okay, so I want to make a remark now. Note that A and B had the same characteristic polynomial, the same eigenvalues, right? But one was diagonalizable, A from the previous lesson, the other is not. Okay, so we're going to have a theorem in the next lesson. One of the statements we're going to make is, if two matrices are similar, we already know that they have the same determinant, that they have the same rank, that they have the same trace. Now we're going to have a theorem that they have the same characteristic polynomial, and they have the same eigenvalues. So similar matrices are really similar. We're going to collect more and more things that they have in common. Nevertheless, all of these together still aren't sufficient for saying they're similar. Okay? So here's an example of two matrices that have the same characteristic polynomial, the same eigenvalues, but they're not similar because one is diagonalizable and the other isn't. If they were similar, then they have to represent the same map. That's what it means to be similar, right? Therefore, if being diagonalizable is a property they have to share, right? That map has to be diagonalizable either for both or for none, right? So let me just write that. Conclude with writing that. Let's erase this theorem. Remark. A from the previous lesson and B from the previous example, from this example, are not similar. Are not similar since A was diagonalizable and B is not. Okay? Is it clear why one being diagonalizable and the other not implies automatically that they cannot be similar? Okay? Because if they're similar, they represent the same map in different bases. Okay? And if they represent the same map, then if that map is diagonalizable, that means both of them are similar to that diagonal matrix D. But one is similar to a diagonal matrix and the other is not. Okay? And this is, so let's write this, since A was diagonalizable and B is not, although, so they're not similar, although they have the same characteristic polynomial and the same eigenvalues. Good? Okay. Good. So what I want to do next is collect a few more statements on eigenvalues, on similarity, and on diagonalization. Okay, a few more statements about these three notions, especially about eigenvalues and how they interact. In particular, we're going to have a couple more statements concerning, remember we had that big theorem, A is invertible, if and only if determinant is not 0, if and only if it has full rank, if and only if its row equivalent to I, if and only if its rows are linearly independent, if and only if for every B, AX equals B has a unique solution. Okay, so we're going to throw in a couple more, one in terms of eigenvalues, one in terms of the characteristic polynomial. Okay, so there are going to be some more statements of that sort, and all of that is going to come up next, and we're going to see how to use these observations or little theorems in order to work out examples, more examples. Okay, so determining when a map or when a matrix is diagonalizable, first of all, we saw it's not always. Okay, it has to satisfy a rather strict condition in order to be diagonalizable. The characteristic polynomial has to factor into linear factors. That means enough alphas. And each alpha has to contribute enough v's. That's the statement that the geometric and the algebraic multiplicities have to be equal. Okay? So if they are, then we know the algorithm, how to exactly calculate the alphas and the v's, and to write the diagonal form, and even the p that does the diagonalization. If they're not, we know how to note that they're not, right? If the geometric and algebraic multiplicity don't coincide, that's it. Okay, good? Okay, thank you. Van